Hi, my name is Kaylin Cummings, and today we'll be discussing Physics Lab 4. This lab had many purposes. One general purpose was understanding physics models. Another general purpose was tracker and coding application. This lab also allowed us to better understand how motion works when there's a mass on a spring. This lab also allowed us to compare motion among observed and predicted models. Multiple principles and models were used in this lab. We viewed Newton's second law, which focused on the force being equal to the change in momentum divided by the change in time, to help us understand the motion we were observing and predicting. The energy principle views the relation between change in energy and surrounding work with thermal energy exchange. This was used to compare the energy fluctuations between that which was observed and predicted. We were able to ultimately observe in this lab that both motions, predicted and observed, were somewhat similar in the x and y values, with this being more true for the x values. The change in energy is zero, confirming that energy is indeed not lost, and the change in kinetic energy fluctuated in varying patterns. The system present consisted of the Earth, the mass, and the spring. The surroundings present were nothing. This is because if we set the system to include all elements that do work on the mass, then nothing in the surroundings does work. Therefore, the W of surroundings would equal 0, and Q would equal 0. The initial conditions were as follows. The ball's mass was 0.402 grams. The ball's position was negative 0.08717, negative 0.603, 0 meters. And the ball's velocity was 0 meters per second, and delta T was 1 over 210 seconds. The constants used include the gravity when close to Earth, which is 9.8 meters per second squared, the spring constant present, which was 6.83 newtons over meters, and the relaxed spring length, which is LO, which is equal to 0.123 meters. The models shown were applied in coding. We use Newton's second law for its many purposes, including being a link between momentum and time, as it is F net equals the change in momentum over the change in time, and we use the velocity update and the position update. This velocity and position update were very helpful as we were watching motion. We also viewed the energy principle, which claims that the change in energy of the system is equal to the work done by the surroundings plus the thermal energy, and this was equal to ultimately 0. Since we're viewing all energy present, we also viewed translational kinetic energy, spring potential energy, gravitational potential energy as well, and we were able to sum these equal to 0. Since the spring was present, we used spring force, and we also used the force of gravity present, and we combined these to give us our net force. Below is a formula that claims that T oscillation equals 2 pi square root mass over K, and this is used to obtain the period of oscillation. Here is an image from our tracker analyzation of a certain video. The blue line is a calibration stick, and the red points are point mass markers. These help us track position. As we can see here as well, there's a mass attached to a spring that is in motion. Here is the code we use to generate the predicted data. The first portion contributes to the creation of the motion visual with a component inside that also generates the spring. We then present the initial conditions. The next portion also contributes to the visualization. We then introduce timing. Starting in the next image, we introduce our constants to be used in models. We then import components of the spring force, followed by a block with information related to energies that we discussed earlier. We then enter the calculation loop, starting with introducing the initial energies involved. We then calculate gravitational force, negative mg in the y direction, followed by spring force. We combine these four components to form net force, as again discussed earlier. In the next block, we use Newton's second law to update velocity and position. Following this, we update the spring values, and then we calculate the changes in energies. The first two components of this image of coding contribute to plotting our data. Finally, we use the next block to compare data, and then we ultimately, at the end of this loop, update time. The code is all finished with an all done print command. Here's the data that we obtained from Tracker. Here are the results we got from Tracker. These results compare the x versus y motion through the observed motion. Here are the beginning results of our coding. The first image shows the motion of the mass attached to the spring. On the right, we also have more coding results. These results explore the change in energy versus the change in time. As we can see, this change in energy is present for delta K, delta U grav, and delta U spring. And we also see the orange line representing delta E. Here we have what is similar to a comparison of predicted motion in the x position versus time and the y position versus time. In reference to the last slide, here are some of the similarities and differences that were present between x direction motion and y direction motion. While the motion in the x direction was decently aligned between the model and the experiment, there was less alignment in the y direction. The x direction experimental models was slightly greater in values than the model. On the contrary, in the y direction, the model had greater or noticeably greater values than the experiment. For both the x and the y direction motion, model values were more consistent, thus producing smoother data. However, also for both y and x directions, the experimental values were more inconsistent, resulting in jagged data. There are many possible errors that could have been present. One could be the misunderstanding of tracker use, which could possibly lead to improper gathering of data. Another possible error would be improper application of models and coding. Now for the what if questions. We were asked if the energy principle was satisfied. We came to the conclusion that it was satisfied because the sum of the changes in energy, kinetic, gravitational potential, spring potential, was all equal to 0. We were also able to notice how similar the values of spring potential energy and gravitational potential energy were. However, they seem to reflect each other across the x-axis. For the final what-if question, we were asked to make two separate estimates of oscillation periods in both the x position and the y position. Now, before doing this, we came to the conclusion that one cycle is the equivalent to the distance and thus the time between two of the peaks or troughs in the position versus time graphs. In order to determine this, we determined that 3t was equal to the total time we would use. And then we divided that by 3 in order to get our value of t. We then found k by using 4 pi squared times the mass divided by t squared was equal to k. As both values were actually the same, we can see that in our experiment there was no impact present in relation to springs.